Hi, students. So today's topics are kind of my favorite topics in chemistry, and we go into the shapes of molecules. The reason why I like this so much is the concept of form equals function. The shape of a molecule influences both its physical and chemical properties. So again, this is still covered in chapter 10, chemical bonding, but now we're going to take everything we did in the first part with Lewis dot structures and apply it to what is referred to as molecular geometry. So the first thing is the concept of valence shell electron pair repulsion theory. So now that we know how to draw correct Lewis dot structures, we can determine from a Lewis structure what the 3D shape of a molecule or polyatomic ion might look like. So the VSEPR stands for valence shell electron pair repulsion theory. Why such a long term? Valence shell. Well, the valence shell, the outer shell, is where we see electrons being either completely transferred or shared in forming both ionic and covalent bonds. Electron pair. We know that bonds are shared pairs and lone pairs are unshared pairs, and they come in pairs. Repulsion, because electrons are negatively charged, they repel each other. And they want to spread out as much as they can in these orbitals. So we're going to take the theory based on electron groups. So we're going to look at the different types of electron groups. There's lone pairs, there's single bonds, and then there's the double and triple bonds. But no matter what, these groups are going to repel each other because they're negatively charged. So the Lewis structure predicts the number of valence electron pairs around a central atom. So we did that previously drawing Lewis structures. And we're going to see that lone pairs count as a group on a central atom. But what a lot of people get confused is that each bond, it doesn't matter if it's a single, double, or a triple, we're going to treat that as one electron group. Okay, so that's only one group, even though there might be more than a pair of electrons. So in this example of nitrogen dioxide, we see that there are actually 3 electron groups around the central atom of nitrogen. So one group is a lone pair. So there's my one group. The other group is the oxygen that has just a single bond, and the third group is the one with a double bond. I just tell people, look at this as I have 2 atoms. Doesn't matter how many bonds the atoms have to the central atom, there's just 2 of them. So between the one lone pair and the 2 atoms, I have 3 electron groups around nitrogen, the central atom. So that is critical. Figuring out how many groups you have is going to help you tremendously. So our focus in this class is, do you have 2, 3, or 4 groups around a central atom? The easy one is 2 groups. 2 groups around a central atom forms a linear geometry and a 180-degree angle. So if I have a central atom and I have 2 things attached to it and I want it to be as far apart as possible, they're going to be 180 degrees. If I have 3 groups, that's referred to as trigonal planar. It forms a molecule that has essentially 3 sides and it's in a flat plane. So you can think of it as if I have a circle and I split it into 3 equal parts, a circle has a central angle of 360 degrees. If I split it in 3 equal parts, each angle here is 120. So the central atom would be in the center, and then I would have 3 groups attached, forming roughly 120-degree angles. With 4 groups, it's tetrahedral. So a lot of people might think, wait a second, 4 groups, wouldn't I have, 2 there, and forming a right angle? You think that because we're looking at the board as a flat plane, 2D. But remember, molecules are in 3 dimensions. There's not just an X and Y, there's a Z axis. So as a result, you get a molecule that can have things coming into the plane of the board and out of the plane of the board. And you create a three-dimensional structure that forms four sides that's referred to as tetrahedral. And the bond angle is actually greater than 90 of 109.5. So 3 terms: 2 groups linear, 3 groups trigonal planar, 4 groups tetrahedral, 3 angles 180, 120, 109.5. So linear geometry. We've already drawn CO2 in the prior videos showing its Lewis dot structure. And when we look at its Lewis dot structure, the central atom of carbon has 2 groups attached to it. So the 2 electron groups are just the 2 atoms of oxygen. So we're going to treat these, it doesn't matter that they're double bonds or single or triple. They just want to get as far away apart as possible from one another. So how do you do that? You form a 180-degree angle. So that makes a straight line. So this is a linear geometry with an angle of 180. What about trigonal planar? We'll look at formaldehyde. We've also drawn the Lewis dot structure for this. Formaldehyde is carbon as a central atom, flanked by 2 hydrogens and an oxygen. But how many groups do I have? So around carbon, I have 3 groups. 1, 2, 3. Again, these electron groups, I'm just going to say they're atoms. I don't really care if they're single, double, or triple bonds. I have 3 groups because 3 atoms. So what are they going to form? 3 groups. I'm going to split it up in a circle, and I'm going to make 120 degrees. That's where I showed you earlier. I have a circle, which is 360 degrees. If I split it up, I make 3 angles of roughly 120. The last one, tetrahedral. So we'll look at methane. We've also drawn a similar structure to this. It has 4 electron groups. So again, when we're doing Lewis dot structures, we might draw it in 2D, thinking perpendicular, and draw CH4 as a structure on the left. But in 3D, to maximize this bond, right, to spread these electrons in the bond as far away apart as possible, we can get an angle greater than 90 degrees. We can get one of 109.5, and we form this tetrahedral structure. Now, even though I'm done with this particular PowerPoint, I want to show you something really useful where you can build on this. So if you guys go online to Google and you type in FET Colorado EDU and do a Google search, you'll get this. Basically, it's a free science simulation, and you can click on chemistry. And when you click on chemistry and you scroll down, you see all these simulations for different things to work on. Now, I like the ones with a 5 because then you don't have to worry about Java or flash drive. That's up to you guys. But what I really want to pinpoint out for you guys is this molecular shapes one. This is going to help you with chapter 10 a lot. And it's also going to help you with your lab experiment 9. So if you click on this, it just takes a second to pop up. You click on that, and you get the FET interactive simulation. And you can go to models, click on models. And then what you want to do, okay, is you want to click on molecule geometry and electron geometry to start. One of the things that I want to mention is if you only have 2 atoms, it doesn't matter what those 2 atoms are. You're going to always have a linear molecule. Just think of it as 2 dots, right? If you connect 2 dots, what do you form? You form a line. So here's 1 dot, here's another, I draw a line. 2 atoms, you're only going to have a linear molecule. Doesn't matter if they're single bounded, like in hydrogen, the diatomic, or if they're double bounded, like in oxygen, the diatomic, or if they're triple bonded, like in nitrogen, the diatomic. It doesn't matter. you're always going to have a linear molecule. Now, our concern is, well, what if I have a central atom with two things attached? So let's do two bonds. If I do two bonds, what do I notice? They're 180 degrees apart, and I make a linear molecule. Now, it doesn't matter if one bond is single and the other is double. It's still going to be 180 degrees. Why? I want to get these atoms of these electron groups as far away apart as possible. So we can also see it doesn't matter if they're both doubles. So here's CO2. They're both doubles. Doesn't matter. We can also use the example of, well, what if I had a single and a triple? Because carbon can have 4 bonds. Two atoms, what do we have? A linear molecule, 180 degrees apart. Now, if I get rid of this, and let's say I form 3 bonds. If I form 3 bonds, what do I get? Trigonal planar, and I get that 120-degree angle. It doesn't matter that one has a double and the other two have single. It's still 3 atoms, 3 electron groups, and it's a 120-degree angle. So what happens if there's 4 groups attached? Now, this is why I really love this simulation. This really shows me what I'm not that good at drawing on a PowerPoint is that 109.5-degree angle. And you guys can mess around with this, but it's showing me that I have the tetrahedral arrangement and I have a bond angle of 109.5. So again, I love this PhET simulation. I would highly recommend playing with this. And thanks for tuning in. I hope this was helpful, and I'll see you guys in the next video.